Hello and welcome to my video, lesson 7.7 on detecting subatomic particles. So we can easily detect subatomic particles using something called a cloud chamber. Cloud chamber is basically when we superheat a liquid to the point where it's about to boil, and all we need to do is add a bit more energy and it will vaporize. Now, if you've never seen this before, you might want to just look up a couple other YouTube videos where people create their own cloud chambers. What people will do is actually use those super cool things. So they're going to cool them into liquids just before the point where they would boil. So if you have liquid nitrogen or maybe dry ice would help you get there or something like that, then there might be a way of going from there and making your cloud chamber as well. But regardless of whether it's a really cold substance or really hot substance, the point is that it's right before the boiling point. So some substances like CO2, for example, have a much lower boiling point. So it is a cold temperature, but we still call it superheating, even though it's a cold, because it's right at the point just before it's about to boil. So all we need to do is add a bit more energy and it'll vaporize that liquid into a gas and we will see the bubbles. So when a charged particle goes through the superheated liquid, it interacts with the liquid, imparting some energy which creates a trail of bubbles behind where the particle was, showing the path of the particle. If we do this inside a magnetic field, we can see these charged particles being deflected by that magnetic field and getting their circular motion paths. And if we could measure the radius of the curve, which is relatively easy, the magnetic field strength, which is relatively easy, and the speed of the particle, which is a lot harder, we could determine the charge to mass ratio in basically the same way as J.J. Thomson's experiment. We normally don't do this, but if you can compare other things, then you can work your way there. So if you know the speed of an alpha particle, and then you shoot it through this cloud chamber, then you could go ahead and figure out its charge to mass ratio. And if you know its charge to mass ratio, and you know that, well, an alpha particle has 2 protons, so it's got a positive 2 charge, and we can compare that to everything else we know about electrons to be able to balance it and whatever, then we can not only know charge to mass ratio, but if we know the charge, we can actually find the mass of an alpha particle, or we can find the mass of a positron or whatever else. And it turns out that it could be useful. We don't see a lot of these calculations show up in Physics 30, but I mean, you could go through and make the centripetal force equal to magnetic force and solve it for whatever you want. And you'll notice like it simplifies to right here, the velocity of the particle over the radius that it's curving and the magnetic field equals the charge to mass ratio. So because it's so hard to measure the speed of the particle, we normally don't see this show up in Physics 30, but it could be. But we could, if we knew the charge and mass, we could reverse and calculate the speed of the particle. So that's probably a little bit more likely to see. Now, there's a few things we need to know when we are looking at these diagrams or pictures of cloud chamber bubble tracks. That is that heavy particles bend less and faster particles bend less. So with that in mind, if you're looking for the circular path and it looks relatively straight, then we know that it's either really heavy or really fast. Okay, and also it's important to know that the hand rules tell us the direction of the particle path. So the fingers are the magnetic field, palm is the force applied onto the particle, and so on and so forth. So if this is the and we should also know that the X means it's going into the page, the dot means it's coming out of the page. So what we need to do here is look at this diagram, and given all the labels that we have, try to see if you can figure out the direction of the magnetic field? Well, so what's happening here is a gamma ray comes in. This is not actually a bubble track. It's just kind of a diagram showing that it's coming in. And it hits some sort of atom over here and really, really excites an electron. So it excites and scatters an electron like this. This is Compton scattering. And it also will release an electron here and a positron here. And so it's a very high energy gamma ray that did this. Now, if this is a scattered electron and this is an electron, that means that negative charges are being pushed in this direction when they're moving in this direction. So my thumb is going to be this one, right? And my palm, which is the force being applied, is in this direction. So with that in mind, if you use your left hand, why is it left hand? Well, because this is negative. So if we use our left hand, then the fingers are pointing into the page, which means if you shoot an arrow into the page, then the magnetic field would be using X's, and so it's going into the page. All right, and so you can see the positron is doing the opposite, so you'd use your right hand for that because it's positive. Yeah. So here are two different questions that you can try to answer. Given the diagram below, which way, or what is the blue track showing? That's right over here. What's that blue track showing us? And what particles are they and what are they doing? Notice the magnetic field directions. All right, sorry. I'm looking at this a little bit more carefully and noticing that everything doesn't really make sense with this part here. It's backwards. So this image is incorrect. I Googled it and got this, but this should be a dot. There should be a bunch of dots showing that the field is coming out of the page and not going into the page. So I'm not really sure what these X's are. And when I read the website a little bit more clearly, they are saying, you know, that the field is coming out of the page. Okay, so with that in mind, this is incorrect, and so are all the other X's, but that's okay. With that in mind, pause the video and try it out yourself and see if you can understand what the green, the blue top, blue bottom, and purple tracks are, and especially what is the blue track, like what is actually happening there to start it. Okay, hopefully you tried it out yourself. Now, if it is coming out of the page, then you're going to point your fingers up, and you're going to use your thumb to show the direction of the motion. The motion is this direction. So fingers up, motion that way, and the palm is pointing at the force because you're pushing with your palm. So this here must be some sort of electron or other negatively charged particle, but probably an electron. This here is also probably an electron. Okay, this here could be a proton, most likely is a proton, or a positron. And this part here looks to me like a proton. And so if you look carefully at the beginning here, you can see that this electron in blue and the proton in blue actually start at the same spot. They start right there. They both have their initial starting point right here. So what's happening there? Okay. Well, what reaction do you get a proton out of it and an electron out of it? You get something else as well, but don't worry about that. What do we have to start? Well, we have a neutron to start. Well, you'll notice here that a neutron has no positive or negative, so it starts as zero charge, and the positive and the negative from the electron and proton cancel each other out. This is a beta negative decay. That's what it looks like to me. Beta negative decay, because it looks like that proton is being launched off. Because protons are heavier, they will have, they'll be affected less by the magnetic field. Okay. Or they could be moving faster, but a faster positron would look very similar to a slower proton. But I think that's what this is, beta negative decay. So why do so many of the bubble tracks look straight throughout a field like this? Because we can't see neutrally charged particles in a cloud chamber. If it's neutral, it doesn't create the bubble tracks and we can't see it. So neutrons we cannot see, or neutrinos we cannot see, or any other neutrally charged atom or element we can't see. So why do they look straight? They should be curving, right? Well, the reason why they look straight is either because they're very heavy, but more likely because they are very, very fast. So many of these particles are traveling very quickly, and so they're being affected less per se by the magnetic field. They actually are affected more, but because they're moving so quickly, it appears like it's curving less. All right. Yeah, so I hope that video helped you better understand the idea of bubble tracks. There's a lot of good resources of other pictures and stuff you can find online, but I hope this video helped you better understand what a cloud chamber is and how to read them. Hope the video helped, and good luck.